Okay, let's continue on from the first part of this lecture. Hopefully I can finish the rest in the second part. So, a spontaneous reaction are those where delta G is negative, generally but not always have a delta H that is also negative, which would make it an exothermic reaction like I talked about earlier in the other video. They also tend to have delta S as greater than 0 or positive, and this will contribute to a negative delta G because we're multiplying the entropy by temperature and then making it negative. Note that a reaction can still be spontaneous and have a net delta G which is negative when delta H is positive or when delta S is negative, but not both. So let's look at some possibilities. So I want you to pause this video here and I want you to mathematically try and figure out the sign of delta G in each of these cases. So if you put in a negative number for delta H and a positive number for delta S, what would be the sign of delta G? Write that down and then write down what that means. On the next slide, I'm going to go through this so that you know what the real answers are, and then I have another graphic to explain. So again, please pause the video here. Okay, now let's go on and see what I came up with. So here's a graphic showing you what's happening. And at the top in this pink area is when delta G is positive, and this would be non-spontaneous. And so if delta H was positive and delta S was negative, it would be non-spontaneous at all temperatures, and this is the temperature here. Here we have delta H is still positive and delta S is positive. And now if I get at very high temperatures, I can make delta S predominate over enthalpy, and I can get it spontaneous at very high temperatures. Here I have delta H is negative and delta S is negative. And if it is at high enough temperatures, it will be non-spontaneous. Once it drops down below a certain temperature, and that would depend on the values for H and S, it will then become spontaneous. If delta H is negative and delta S is positive, at all temperatures it will be spontaneous. So what would that look like in your table? So when delta H is positive or negative and delta S is positive, yes, it is spontaneous. Delta G is negative and it is positive, or it's negative at all temperatures, so it's spontaneous at all temperatures. If delta H is positive and delta S is negative, delta G is positive at all temperatures, and so it is never spontaneous. If they're both positive, it could be positive or negative, and it would be negative at high temperatures, so that the temperature, by multiplying this value by T, can make this term large enough to be greater than delta H, making delta G negative. And here the reverse is true. As the temperature decreases, then it would be spontaneous. Okay, so calculate the temperature at which the spontaneity of a reaction changes from spontaneous to non-spontaneous or non-spontaneous to spontaneous. The key is to set delta G equal to 0. And then you can say delta T, or T delta S is equal to delta H. And then you can divide delta H by delta S, and then you could figure out the temperature at which it would be 0. And then if it increases or decreases, depending on whether delta H or delta S was negative, you could figure out at what point it would be spontaneous. We are interested in the change in free energy, and we can look those values up as well. We can just look up straight old delta G if we need to. You will be given data for any problems, and you know I'm going to work out problems for you in class as well as on a video or 2 or 3. And so We do have to remember to pay attention to delta H is in kilojoules and delta S is in joules. So we need to make sure we're using the right units and that they match. So it's important for you to use units in all calculations. So the standard free energy of formation is just like the standard free energy of enthalpy, standard enthalpy, standard entropy of formation, all of those things. And we've discussed those some in this unit, and we can look those up in a table, and we can calculate for any reaction we have the delta G's of formation for. So here is our equation. M moles of A plus N moles of B gives us X moles of C and Y moles of D. And so again, we do products minus reactants, and each delta G is multiplied by the number of moles, and you can see how that works out. And we do this the same for delta H. So this is not a different calculation, it's just a different value we're getting out. So if that value is negative, then it would be spontaneous for the forward reaction. Delta G for any element in its most stable form at standard conditions is defined as 0, just like delta H. That is not true for entropy, but it is true for enthalpy and free energy. So you can look those up in a table. The free energy of reactions, if we have 3, if we want reaction 3 and we can find it for reaction 1 plus reaction 2, just like enthalpy, we can add those two together and get delta G. And that's because this is a state function. Keep in mind, if we reverse the reaction, we have to reverse delta G. If we multiply by a factor, then we have to multiply by that factor for delta G or divide. Same as enthalpy. So that takes care of it. Thanks.